Okay, so next up we have Alex McCleary. He's going to tell us about latest results on functoriality and generalized persistence diagrams.
Yeah, thanks, Amit.
I should say you're at Ohio State now, right? You're a postdoc
that's right.
at Ohio State.
Yeah, so this work is really an extension of what Amit was talking about before, especially in particular the functoriality. So really the main things we did is well, this project started out as the goal was to extend the birth-death function from filtrations to persistence modules. Right, because the birth-death function is defined via cycles and boundaries, and those make sense when you're working with filtrations, but aren't immediately clear when you're working with persistence modules. But one side effect of this approach is that it allows us to tighten up the edit distance between filtrations. So for example, before, the edit distance between filtrations was only defined for filtrations of the same simplicial complex. Now we can loosen up that definition a bit and make it defined for any two filtrations of simplicial complexes with the same homotopy type. So next, we also sort of stumbled on these relationships between well, the birth-death function and the persistence diagram obtained via the birth-death function and the persistence diagram obtained via the the rank function. And we accomplished this by using a new function, the kernel function. Yeah, and then finally, we sort of reinterpreted everything in terms of Galois connections. And this turns out to actually be well, in my opinion, the right language for this setting. Okay, so just some preliminaries. So first of all, we want to talk about posets of intervals. So for this talk, we're going to be focused on just finite posets with a metric. We can extend this to the locally finite setting, but it comes at a cost. I may go into that later if there's time. Okay, so if we have a finite poset, and we're just going to assume there's a metric, we're not going to use that metric until the end, but just leave it there. Okay, so if we have this finite poset, we can talk about its poset of intervals. So there are two orderings on this set here. The first one is the product order, and the next one is the reverse containment order. So the product order is the natural domain of the birth-death function, while the reverse containment order is the natural domain of the rank function. Okay, so now we're going to get into Galois connections. So these are really, in my opinion, something that is quite fundamental to this approach to persistence. So if we have two finite posets, P and Q, a Galois connection between them is just a pair of order preserving maps F and G, satisfying this relationship here. Now, if you're familiar with categories, if we view the posets P and Q as categories, a Galois connection is nothing but a pair of adjoint functors. And so here we're going to talk about F as the left adjoint and G as the right adjoint. Okay, so if we have, Galois connections can be composed. If you have a Galois connection between P and Q, and then a Galois connection between Q and another poset R, we can compose that to get a Galois connection between P and R. And then a Galois connection between P and Q extends to a Galois connection between their posets of intervals. Okay, so we're going to talk about pushbacks and pullbacks and push forwards now. Yeah, so if we have a function f from P to Q, and then we have an integer valued function on P, note that, functions m and n. So m from p to z, n from q to z. These functions do not need to be order preserving. These are just any two functions on p and z. We can push forward m and pull back n along f. So the pullback of n is just given by precomposition. And the push forward of m is given by this formula here. So this might look a little familiar from Amit's talk before. And this is actually push forwards are essentially morphisms between persistence diagrams. Okay, so we're going to come back to that in a second, but for now we're going to go to Mobius inversion. So on any poset P, we can talk about a zeta function. And this is going to be the matrix. It's going to be 1 if A is less than or equal to B and 0 otherwise. Now the zeta function, it has an inverse matrix, mu. And we can use this matrix mu to get the Mobius inversion. So the Mobius inversion is the unique function that satisfies this formula here. And we can use the Mobius function to obtain our Mobius inversion here. So the Mobius inversion of M is just the matrix multiplication, M times mu P. Okay, so this lemma here is really the key lemma for really this whole approach. So this lemma actually turns out to be just a generalization of that functoriality that Amit was talking about in the last talk. And we actually recently discovered that this lemma is equivalent to Rota's Galois connection theorem. So the setting is we have two posets P and Q, and then we have a Galois connection between them. So G is the left adjoint, or G is the right adjoint, and F is the left adjoint. And in this setting, what we get is that essentially the Mobius inversion commutes with the Galois connection here. So this lemma really is the same thing as the functoriality in the last talk. However, it's extended a bit because here we don't need to be working with lattices, and F and G need not be bounded lattice maps either. And so we can actually obtain Rota's Galois connection theorem from this just by plugging in an indicator function. Right, so if we plug in the indicator function 1 sub p, so this is just the function that's 1 if x equals p and 0 otherwise, and we evaluate both sides at a point, we get this equation here, this is Rota's Galois connection theorem here. So this is a really famous theorem in algebraic combinatorics, and was incredibly useful in a lot of 20th century algebraic combinatorics, and it really turned out to be equally useful in this setting as well. Really, all of our results followed pretty quickly from this lemma. So in particular, we get stability out of this lemma, but also all of the relationships between the different persistence diagrams here come straight from this lemma. And it all just comes down to picking the right Galois connection, and then everything falls out of that. So yeah, this lemma was just incredibly useful for us. And I think it's a really nice statement. Oh yeah, and now, so here plugging in indicator functions, this allows us to go from our lemma to Rota's lemma. But since indicator functions form a basis for all functions for all integer valued functions on P, we actually get that the two results are equivalent. So really this lemma here is actually the same thing as Rota's Galois connection theorem. Okay, so now we're going to move on to persistence modules and diagrams. So a persistence module is just going to be a functor from a finite poset P into the category of vector spaces. So these are finite dimensional vector spaces over a fixed field K. So this is an example here. And yeah, and so the maps here are just the projection maps. And now, so we're going to look at a special type of persistence module. So these are going to be the well, really, these are going to be free persistence modules, but yeah. So whenever we have a point A in our poset P, we can talk about the persistence module K to the upset of A. So this is the persistence module that's, it basically is always K at or above A, and it's 0 everywhere else. And all the maps are either the identity or the 0 map. So a persistence module is free if it's a direct sum of these persistence modules here. So for example, this is a free persistence module here. Now, the reason we're talking about free persistence modules is because they're going to allow us to define the birth-death function more generally. Right, so we're going to use these free persistence modules to define the birth-death function by looking at free presentations. So a free presentation of a persistence module is just a surjective natural transformation from a free persistence module to a right. So if you start with the persistence module M, a free presentation of it is just a surjective natural transformation from a free persistence module F onto M. So yeah, every persistence module has a free presentation, but they're not going to be unique at all. And because we're going to use these free persistence modules to define a persistence diagram, that poses somewhat of an issue, but it turns out everything is fine because we want these persistence diagrams to be uniquely defined. It turns out that they are up to stuff along the diagonal. Right, so we can, now define the birth-death function. So the birth-death function of M with a free persistence module phi is the function M sub v, and it's just defined as right. So M sub phi of AB it's the dimension of F of A intersect the kernel of phi of B. So you want to think of this as sort of everything that was that is alive at or before A and dead at or before B. Of course, the analogy here breaks down a little because right, you can always throw in extra stuff into your free presentation and get stuff that is alive at A that isn't really in your persistence module. But it turns out that when you take the Mobius inversion here, all of that extra stuff just cancels out. Okay, so yeah, so the next invariants we're going to cover are the rank function and the kernel function. Right, so the rank function is sort of the classic way of defining persistence. In fact, when Carlson and Zomerodian put out their paper on multidimensional persistence, they proposed the rank invariant as an invariant for multi-parameter persistence. And another common invariant that you see in multi-parameter persistence is the fibered barcode. And it's well known that the two are equivalent. And really the equivalence there is just a Mobius inversion. Applying the Mobius inversion to the rank function gives you what is essentially the fibered barcode. And then you can go the other way by just multiplying by the zeta function. And it's also well known that in the 1D setting, the Mobius inversion of the rank function is the same as the Mobius inversion of the birth-death function up to a shift in the death coordinate. But yeah, so it's one of the goals of this project is to work out what's the relationship there, not in the 1D setting over any poset. And so, yeah, to do that, well, let's first just talk about the rank function. So the rank function is just, it takes an interval AB to just the rank of the map from M of A to M of B. And now we can also define the kernel function, right? So the kernel function is defined analogously. It's just, it takes an interval AB to the kernel of the map between M of A and M of B. And so we can use each of these. Really, we've talked about three functions so far: the birth depth function, the rank function, and the kernel function. We can use each of these functions to define a persistence diagram. And of course, since we have the rank nullity theorem, we get that the rank and kernel functions are related by these formulas here, right? This is nothing but the rank nullity theorem. And so, oh yeah, so, oops. Yeah, so these formulas here are going to give us, well, actually, in particular, this formula right here is going to give us the rank function, or is going to give us a formula for converting between the rank function and persistence diagrams obtained via the rank function and persistence diagrams obtained via the kernel function. Okay, so yeah, persistence diagram. So now that we have these three functions here, we can turn each of them into a sort of persistence diagram by applying the Mobius inversion. So we want to take the Mobius inversion of the rank function with the reverse containment order. The reason we use this order here is because, well, it gives us the normal notion of persistence diagram in the 1D setting. We want to take the Mobius inversion of the birth-death function using the product order. And the reason we use this order here is, again, because it gives us the normal one parameter persistence diagram in the 1D setting. But now we also want to take the Mobius inversion of the kernel function with the product order as well. And the reason for that is that the persistence diagrams of the kernel function and the birth-death function are actually the same off the diagonal. So that means this persistence diagram of the kernel function here is actually going to be the same as the persistence diagram of the rank function or the birth-death function in the 1D setting, at least off the diagonal, and up to a shift in the death coordinate. Yeah, the reason we have that shift there, so is that the Mobius inversion of the birth-death function is capturing when was the first spot a homological feature died, whereas the Mobius inversion of the rank function captures where is the last spot that homological feature was alive. So the death coordinates are just shifted by one, but it's not really a significant difference. So really in the 1D setting, these are all in a sense equivalent. Yeah, and so this is what I was saying earlier, that these two persistence diagrams are identical off the diagonal. And then, yeah, this notion though, that these two persistence diagrams are identical off the diagonal is really important because this persistence diagram right here does not depend on the free presentation we pick, whereas this one does. So that tells us that if we choose different free presentations, we're going to get the same persistence diagram, at least up to stuff along the diagonal. And now we also get a formula for converting between the rank function persistence diagram and the kernel function persistence diagram. And this is just obtained by applying that key lemma to the rank nullity theorem here. And it looks like this. And so this formula is a little messy, but really what this formula boils down to is just matrix multiplication by an invertible matrix, right? You can pull the partial kernel M and partial kernel M here out. You can factor that out. And what you get is just matrix multiplication with an invertible matrix here. So this formula is actually pretty easy to work with. Okay, so now we can talk about categories of persistent modules and diagrams though. So this is sort of extending what Amit was talking about before. So for us, our objects are still going to be just persistence modules. And so these are persistent modules over all finite posets P. We're not fixing a finite poset here. And then a morphism between two persistence modules is given by a right adjoint. Yeah, so a morphism is given by a right adjoint G, such that M precomposed with G is naturally isomorphic to N. Now, persistence diagrams are also a category where our objects are just set maps from a poset of intervals into the integers. So these aren't order preserving or anything. These are just set maps. Now, morphism between two persistence diagrams are given by this formula here. So Amit talked about this in the last talk, so I'm not going to go into this very much. But really, what these are just push forwards. And so that key lemma says that applying the Mobius inversion to either the birth-death function or the kernel function is functorial here. It doesn't work on the rank function, unfortunately, but it does work with either the kernel function or the birth-death function. Okay, so now we can talk about edit distance. So the edit distance we can define on really any category with a weight function on its arrows. So if we have a weight on arrows, we can look at a path between two objects. So this is just going to be a sequence of morphisms with the morphisms going in either direction. And then each of those morphisms has a weight. So we can sum up the weight of all the morphisms and get a notion of length of a path. And then we can define the distance between two objects as the length of the shortest path. So now we can use this to define an edit distance on persistence modules and persistence diagrams. So this is done via the distortion. So if we have a function f from p to q, in our setting, these will be these functions will be parts of a Galois connection, but that's not so important. We can define its distortion. So this is just essentially capturing how much does f stretch points in p as they map into q, stretch or compress. And now really we're working with Galois connections here. So we want to define the distortion of a Galois connection. And this is just going to be the max of the two adjoints, the max of the distortion of the two adjoints. So now we can use this here to define an edit distance on persistence modules and on persistence diagrams. And then Rota's Galois connection theorem, which is the same as that key lemma, says that this assignment is one Lipschitz here. All right, and that's everything. Any questions?
Yeah, thanks, Alex.
I have one question. If you,
Go ahead.
can you show again the formula for distortion of the Galois connection that you?
Yeah.
Somehow I suspect that because you have two maps, that there's an extra term that should appear in the distortion of a pair of maps. Co-distortion, doesn't it show up in your stability proofs? Or? Well, maybe this is something that we can discuss later, but yeah. In general, whenever you have two maps pointing in opposite directions, there's a third term, which is a co-distortion of maps.
I see. Yeah, I don't think that's necessary here. So it's not necessary to get stability. It might be necessary to make the edit distance behave a little better.
Mm-hmm. Okay.
It's not necessary for stability.
Thank you.
Yeah, so I think Luis was next. Sorry, I can't hear you.
Can you hear me?
Yeah, I can hear you now.
Okay, sorry. I don't know if you can hear me very well, but I'll try to be clear. So thank you for the talk. So now that you have basically a persistence diagram that is defined for any persistence module, you don't even need the filtration, and it's multi-parameter. And this is stable in the sense of the edit distance. So I'm wondering, like, do you have some sort of lower bound for the edit distance that you can compute? Time, basically?
No, not right now. So the eddy distance is not very computable in general, but it is, right, because I think like a special case of it could be used to compute the lattice isomorphism problem, which is hard. I'm not sure how hard, but yeah. But there could be some lower bounds that could be easier to compute, but I don't know of any.
Okay, is that something you're working on?
No, not right now.
Thank you.
Tamal?
Hi, Alex. Yeah, I was just wondering, can you say something about what is the advantage of considering the birth date function in place of rank function? I understand, and in 1D doesn't make much difference, but in multi-parameter setting, where will you get some advantage by considering some other function?
Yeah, so the real advantage is that the birth death function is functorial, while the rank function is not. And really what it boils down to is that, so a Galois connection, so if you have a Galois connection between two posets P and Q, that's going to extend to a Galois connection between, so let me see. So yeah, a Galois connection between P and Q extends to a Galois connection between their posets of intervals with the product order, but not with the reverse containment order. Yeah, so that's really the main issue with the rank function, is that its natural domain is the poset of intervals with the reverse containment order.
I see.
Galois connections don't really work very well on that poset.
I see. Thank you.
And then Alex?
Hi, can you hear me?
Yeah.
Yeah, thanks for your talk. I have two questions. First of all, do you have codes to compute the persistence diagrams over finite posets? And
yeah, so Amit and Dimitri worked on that, and there's a paper in the archive.
So that's one of the big open problems I started with. I think we need some good algorithms in that direction.
so you have the codes on archive already?
There's a paper, there's no code available yet.
So, but you have an algorithm?
Yes.
I see. And my second question is, do you have any good idea how one may visualize the diagram of a possibly pretty complicated poset?
Yeah, so really you could visualize it as just a normal like persistence diagram, because really these are just pairs of points. So just like you would a normal persistence diagram, except if you have a complicated poset, it might be really messy and hard to visualize, and there isn't really a good way around that.
I see. Thank you.
Yeah, thanks, everyone.
I think we should maybe move on now to the next talk. We do have 20 minutes. We do have a 20-minute break after Bay's talk, so I think we can discuss more then.
Before moving on to the next talk, should we stop the recording or like, are we splitting the talks? I was not sure.